Welcome to Topology Lesson 10, Metric Spaces, Completeness, and Products. Most of the lecture is on complete metric spaces. Then we have a few slides at the end concerning the product of metric spaces, which are also metric spaces. Consider the metric space 0 to 1 with the Euclidean metric, not including the point 0 and 1. The adjacent points in the sequence 1 over n get closer and closer as n goes to infinity. In fact, the sequence converges to 0, but since we left 0 out of our metric space, it converges outside of the metric space, or we could say the metric space is incomplete in the sense that we have a convergent sequence that doesn't converge in the metric space. Another example of an incomplete metric space is the open unit disk. So we have that defined here. And notice we've excluded the boundary. It's just less than 1. And so there are many sequences in the disk that converge to a point on the boundary, but again, we've excluded the boundary so they don't converge in the metric space under consideration. I just gave one example here, 0, n over n plus 1. So these points get closer and closer to 0, 1 as n goes off to infinity. They also get closer and closer to each other as n goes to infinity, but they don't converge in the metric space itself. So what we have here, these are Cauchy sequences because the difference between the points gets closer and closer, and we have a definition here. In general, the sequence x sub n in the metric space x is a Cauchy sequence if the distance between x sub m and x sub n approaches 0 as both m and n approach infinity. We can write that a little bit more precisely. Sequence x sub n equals 1, 2, 3 to infinity is a Cauchy sequence if for any epsilon greater than 0 there exists a positive integer n such that the distance between x sub n and x sub n is less than epsilon whenever m and n are greater than n. So this is a little bit tricky because it doesn't say n and n plus 1. In other words, two consecutive terms. This could be m and n could be separate by a million terms, and we still want to be able to find an n such that the difference gets less than some given epsilon. So that's a more stringent condition. We'll see an example where that doesn't work on the next slide. So let me repeat the definition of a Cauchy sequence here at the top of the page, since we're going to use that in a counterexample. There's a subtle point that you notice here the m and n are not consecutive, and that's important in the definition of a Cauchy sequence. So these indices could be far apart, but you still have the same condition that they're equal some n, so that whenever you're bigger than this n, regardless of what m and n are, they could be a million units apart, you could still be able to force this distance to be less than e as long as you're bigger than some n. So we have an example here where the distance between consecutive terms goes to 0 as n approaches infinity for this sequence here, the square root of n, but the sequence doesn't even converge, let alone it's not a Cauchy sequence either. We can see that by taking the difference of these two consecutive terms, just using the Euclidean distance here, and we plug in square root of n plus 1 minus square root of n. We multiply the top and the bottom by this term here and here. In the top, if you multiply this out, you just get 1. And then notice on the bottom, the square root of n plus 1 is greater than the square root of n, so we can replace this by the square root of n. And that means this is less than 1 over 2 times the square root of n. But so this goes to 0. The distance between these two terms goes to 0 as n goes to infinity. However, as n increases, the terms square root of n become arbitrarily large. We know that. This blows up to infinity. So for any index n and distance r, there exists an m sufficiently large such that the square root of m minus the square root of n is bigger than that some r, which means we can never find this n that we're looking for to show that it's a Cauchy sequence. And of course it's not. So we have a counterexample, and again, we need to be careful about this definition here, and especially this m and n. They're not consecutive. The definition of a complete metric space is one in which all Cauchy sequences converge to a point within the metric space itself. The advantage or the utility of Cauchy sequences lies in the fact that in a complete metric space, the criterion for convergence depends only on the terms of the sequence itself and does not require knowing the limit of the sequence. So we know the definition of the Cauchy sequence just is that the difference between x sub m and x sub n goes off to 0 as m and n go off to infinity. So we don't actually need to know the where they approach, the exact limit, which may be helpful in some problems. So we have a couple of examples. I'll give you a few more later on, but we have the real numbers are a complete metric space, and then n-dimensional Euclidean space is also a complete metric space. We have a theorem here also. A convergent sequence is also a Cauchy sequence. So convergence implies Cauchy sequence. Let's see, that's pretty easy to prove. Let's take x sub n, the sequence x sub n, which converges to x in some metric space, capital X. So that's the assumption in our theorem. Then by the triangle inequality, we have the difference between x sub m and x sub n is less than the difference between x sub m and x plus the difference between x, the distance between x and x sub n. And as the right-hand side of the inequality approaches 0, as m and n approach infinity, that's because this sequence converges to x. So if these two terms go to 0 as m and n approaches infinity, then of course the distance between x sub m and x sub n also goes to 0, and that proves that it's a Cauchy sequence. Let's talk a little bit about subsequences of Cauchy sequences. So first, let me define a subsequence. It's just a subset of a sequence minus some terms. I have an example here. We have the sequence 1, 1/2, 1/3 out to infinity, and we have a subsequence where we remove the terms that have an even denominator. So we have 1, 1/3, 1/5, 1/7, and so on. So the bottom sequence here is a subsequence of the thing on the top. The main thing is that it has the order. You need to keep, even though you're removing terms, you need to keep the same order. So our theorem is that if a subsequence of a Cauchy sequence converges to x, then the entire Cauchy sequence also converges to x, which may seem obvious. So in other words, if in this example up here, this subsequence all converges to 0, and if you believe the theorem, which is true, then it would say that this containing sequence, this larger sequence, also has to converge to 0. It seems kind of obvious, but it needs to be proved. So let's do that. It's not too hard. Let's let x be a metric space and x sub n be a Cauchy sequence with the subsequence x sub n sub k that converges to x. So that's the our assumption here. What we want to do is show that x sub n converges to x. In other words, the whole sequence, rather than just the subsequence, also converges to x as n approaches infinity. Since x sub n is a Cauchy sequence, by definition, for every epsilon prime, which we're going to let equal to epsilon over 2, you'll see why I'm doing this little odd misdirection here. So for every epsilon over 2 greater than 0, there exists a positive integer n, such that for every n and m greater than n, we have that the distance between the x sub n and x sub m is less than epsilon over 2. Okay, so that's by definition of a Cauchy sequence. Then by hypothesis, there exists an L greater than 0, such that for all n sub k greater than L, we have that the distance between x sub n sub k and x is less than epsilon over 2. That's because we said that this subsequence converges to x. So we have these two things. Now, if we pick any epsilon greater than 0 and we require n, m, and l to be greater, n, m, and n sub k to be greater than the maximum of n and l. So here we have n, m, and n sub k greater than m, where m is the maximum of n and l, then these two things hold true. If we use the triangle inequality, we have the distance between x sub n and x is less than the sum here, again by the triangle inequality, and then we just plug in epsilon over 2, so we're less than epsilon. So this is basically the definition of the convergence of the sequence x sub n converging to x as n goes to infinity, which is what we wanted to prove. On this slide, we're going to show the relationships between closed and complete. I have this theorem from our previous lesson. I'm going to use that in a minute. I just put it up here as a reminder. So the first theorem is a closed subspace of a complete metric space is complete. So closed implies complete if you're in a complete metric space. So to prove this, let Y be our closed subspace, and let X be our complete metric space. Let Y sub n be a Cauchy sequence in Y, and consequently it's also a Cauchy sequence in X. That's just because Y is a subset of X. Since X is complete, Y sub n converges to some Y, an element of X. But if you have a convergent sequence in Y to some little y, then that little y, from this theorem 69, that little y has to be adherent to Y. It's not necessarily an element of Y, but it needs to be adherent to Y. However, we're told that Y is closed, and so a closed set contains all its adherent points, and so Y is an element of Y. And so we've shown that every Cauchy sequence in Y converges to a point in Y, and thus Y is complete. So that's our first theorem. Then we can go in the other direction. A complete subspace Y of a metric space is closed. Let's prove that. And first note that for a set to be closed, it must equal its closure, and that in turn means that it must contain all its adherent points. That's just definition. So let's take any point in X that's adherent to Y and show that X is an element of Y, and then that'll effectively show that Y is closed. So this means for every R greater than 0, by definition of adherent, that there is an open ball about X, a radius R, that intersects Y, and there's some element, it's not empty, so there's some element in this intersection. Then what we do is take a series of R's, smaller and smaller, 1, then 1/2, 1/3, and we form an open ball of each of these different radii. So for each one, since we know they're non-empty, we know there's some representative X sub n in each one of these open balls intersected with Y. Further, we know that the xn's are also in Y. So we have the xn's converge to some x, the x we picked here, surrounding x here. So the x sub n's converge to x as n approaches infinity. By theorem 75, we know that x, the series x sub n, is a Cauchy sequence. That's because a convergent sequence is a Cauchy sequence. That was the theorem. And since these are all, each of the x sub n's are in y, we know that, and y is complete, we know that this series x sub n converges at some point y and x, y, little y and y. And we also know from theorem 68 that the limit of a sequence is unique. So this y must equal that x. So y, little y is in our capital Y, and we've shown that any point adherent to y is also an element of y, and that means that y is closed. This slide and the next few slides concern a concept known as dense. And I want to give you an analogy before I start. If someone tells you that a forest is densely populated with trees, you wouldn't think that every square inch of the forest floor has a tree coming out of it, but you would think that you can't go very far without running into a tree. You probably wouldn't be able to drive a car through it. Maybe you might be able to walk through it with some trouble, but the idea is that it's very full of trees. And so we have something similar for topological space. A dense subset of a topological space means that subset is pretty much almost everywhere. You can't go very far in terms of distance without running into an element of the subset. So we have a more formal definition. Actually, we have several equivalent definitions. Let me go through those. A subset Y of a topological space X is said to be a dense subset of X if any of the following conditions are satisfied. So the first condition, the smallest closed subset of X containing Y is X itself. The closure of Y equals all of X. The interior of X when you remove Y is empty. So once you remove Y from X, there's almost nothing left. The interior itself is empty. Every point in X either belongs to Y or is a limit point of Y. And then the intersection of Y with each non-empty open subset U of X is non-empty. So Y would, if you take any open set in X and you intersect it with Y, you're going to have some elements in that intersection, if in fact Y is dense in X. As a first example, we have the rational numbers being dense in the reals. Remember, the rational numbers are just fractions, and the reals are any possible number, including things like pi and fractions, or I should say things that have an infinite non-repeating decimal numbers after a decimal point. So we can prove that. Q is usually Q is used to represent the rational numbers and R the real. So the proof comes in two parts. We're first going to show that between any two real numbers there's a rational number, a fraction. There's two cases for that. Let X and Y be real numbers. Assume X is less than Y, and consider Y minus X. If the difference between Y minus X is greater than 1, then there's an integer between X and Y. And so and of course an integer is also a rational number, so that would prove our statement here. And the second case is when Y minus X is less than 1, but all we need to do is multiply by an integer to make Y minus X greater than 1, and then we have ny minus nx satisfying our first case, which means there is some integer m between nx and ny, and then we just we divide by n, and we get x is less than m over n less than y, and of course m divided by n is an integer, so is a rational number, a fraction. So we've proven that in the second case. So we're almost done taking this result here. Take any real number x and another real number x plus epsilon. We know from what we've proven up here that there's some rational number, we'll call it r sub epsilon, that's between x and x plus epsilon. And then using an idea similar to the proof of the last theorem on the previous slide, we just let epsilon equal 1, 1/2, 1/3, and we get a whole sequence of rational numbers, r sub 1, r sub 1/2, r sub 1/3, and so forth. And they converge to x since we're making the epsilon smaller and smaller as we go along here. And by theorem 69, which I've copied again for our convenience down here, the sequence converges. This is a convergent sequence, and since it's a convergent sequence, it's adherent to y. In this case, y in the theorem is our set of rational numbers, and so we've taken any real number x and we've shown that it's adherent to Q. In other words, the x is in the closure of Q. So that implies that the real numbers equal the closure of Q, which is the closure of the rational numbers. And that was one of the, if you recall, that was one of the equivalent definitions of dense from the previous slide. Let's look at a few examples. We have the one from the previous slide. Rationals are dense in the real, and in fact they're a countable dense subset, which is interesting. So they can be put in a one-to-one correspondence with the natural numbers, 0 or 1, 2, 3, 4, 5, 6, 7, so forth. So that's interesting. Then the irrational numbers are an uncountable dense subset of the real numbers. And the rational and the irrationals are kind of intertwined very tightly, and the implication is that neither has each has a empty interior. They have no interior points. So no matter what open ball you put around either a rational or an irrational, you're going to get points that are not in the given set. And that shows that dense subsets need not contain any non-empty open subsets. So another example is the open interval from 0 to 1 is not dense in the metric space R. It's kind of easy to see. I mean, you can take a point like 2, 3, 4, 0, 1 comes nowhere near any of those points, so it's not dense. However, the open interval 0, 1 is dense in the metric space, the closed metric space from 0 to 1, and we can see that the closure of the open interval 0, 1 is in fact equal to the closed interval 0, 1. So dense does depend on the enclosing set for your subset. The set of integers is nowhere dense in R. In general, a subset Y of a metric space is said to be metric space S. X is said to be nowhere dense in X if its closure has no interior points. In other words, if the interior of the closure of your subset Y is equal to the empty set. And then we have a somewhat different example here. If we take any complex valued continuous function, for example, the sine of z plus 3 times the cosine of z, the hyperbolic trig, the complex hyperbolic trig functions added with the sine of z, for example, you can take anything like that, and it can be uniformly approximated with a complex polynomial function, which is kind of surprising, but as I say, it's a known theorem. It's called the Weierstrass approximation theorem. And so in other words, the polynomial functions over a closed interval, the complex polynomial functions over a closed interval are dense in the space of continuous complex valued functions. So we're not going to, don't get worried, we're not going to get into complex variables in this particular lecture series, although I do have one on complex analysis. But I just wanted to give you a kind of a different example here. In the next few slides, I have several theorems where I don't provide a proof, but I think they're important enough to at least state so you have the information in terms of the theory, the theorem itself. The proofs are a bit complicated, but I do have some references if you're really interested in seeing the proofs. So let's do this first one here. It's called the Baire category theorem, spelled B-A-I-R-E. Let me use the pointer here. And that gives sufficient conditions for a metric space to be a Baire space. And what is that? Well, a Baire space is a metric space such that the intersection of countably many dense open balls is still dense. So key thing here is intersection. So if you have a countable number of dense open sets, the intersection of all those is still dense, and we can just state it here a little more formally. So if y sub I equals 1, 2, 3, so the collection, a countable collection of dense open subsets in a complete metric space X, then the intersection of all these subsets is also dense in X. So that's probably not obvious to me for sure that you have these dense subsets, which are when you take the intersection, you're still forced to have a because when you take intersections, you get less and less, right? Not everything is in the intersection. So, and it's not just a finite; it's a countable collection of these, and still you're forced to have a dense subset of an X, which is interesting, to say the least. So the proof is in the Wikipedia article. It's called entitled Baire category theorem, and it has two general forms of the theorem, and the proof of they have some letters to indicate the different forms. So the proof of the form known as BCT1 can be applied to metric spaces. So again, if you're interested, it's free. You just go to Wikipedia and have a look at that. But again, I think it's worth just noting this theorem. It's a rather important result in metric spaces. So we defined nowhere dense before, but let me just put it up here to remind us. So a subset Y of a topological space is said to be nowhere dense or rare if the closure has an empty interior. In other words, int the Y closure equals an empty set. So if we took the integers within the real numbers, the closure of the integers is just the integers again. They're isolated points, so the closure is just the integers, and that has no interior, so the integers would be nowhere dense in the real numbers. In fact, any finite set would be nowhere dense in the real numbers. We have a theorem related to this idea. So a subset Y of a metric space X is nowhere dense in X if and only if X minus the closure of Y is a dense open subset of X. And in my book I give a reference to a proof. It's from something called Math Stack Exchange. That's an online resource where people ask questions and experts give answers. So if you go to my book, you'll see it's reference 82. I have a link to that proof there. Then if we take the complements of sets in Baire category theory from the previous slide, we get this version. If Y sub I is a countable collection of nowhere dense subsets in a complete metric space, then the interior of the union of all these nowhere dense subsets is still empty. So by taking more and more, the union of more and more nowhere dense subsets gets you nowhere. At least if it's a countable collection, you're still going to get an interior that's empty. Let's change gears a little bit and talk about the product of metric spaces. I could have put this in a separate lesson, but there's only 3 slides, so I decided to put it in with the complete metric spaces lesson. The product of metric spaces is a Cartesian product, which I'll explain in a second. So let's take n metric spaces here. They could be the same. In other words, these could all be the real numbers with the Euclidean metric, or they can each one be different, or 2 of them could be the same and others could be different. So any combination is valid as long as these are metric spaces. And then the elements in the Cartesian product is basically n tuples. So you have one element from x1, one element from x2, and so on all the way down to xn. So it's that's fairly easy. Then the question is, well, what does the distance between these elements in the set look like? And there's different possibilities. One possibility is something called a p-norm, and I'll show you some examples of that. So here's an example. So we have x1 to xn, so that's one element from the product, and then y1, y2, so forth to yn is another element from the Cartesian product of our n metric spaces, and we define the distance on a term-by-term basis. So we use the first metric just to get the distance between x1 and x2, and we raise that to the p power, and then we do the same for x2 and x3, and so on all the way down to xn, in each case using the metric between the elements of the given metric space. We raise it to the p power, and then we take then we add these together, and then raise the whole thing to 1 over p. And p could be any number, any real number from 1 to infinity. And when p is actually equal to infinity, we define it this way here. It's just the max of the distances between each term here, x1, y1, x2, y2, all the way to xn, yn. So I'm not going to prove this is a metric. Remember, we had 4 properties. It only equals 0 if the 2 elements equal 0. If the 2 elements are different and it's greater than 0, we had the symmetry, which actually that's kind of obvious here, since each one of these are individually have the symmetry property. Then the triangle inequality is always the one that's a bit hard to prove. Yeah, so here's an example of a product. The Euclidean n space can be constructed as the product of n copies of the real numbers, each with the Euclidean metric, and using the p-norm, p equals 2. So you would just have this one squared, this one squared, and then you take the square root of the sum. So we've seen that type of norm previously. So that's one example. Let's continue on the next slide. Let's continue with our discussion of product metric spaces. Consider a product metric space, as we defined before, x sub 1 cross product x sub 2 and so forth to x sub n, where these x's are metric spaces. And then let's say we have an infinite sequence in each one of these. So we use this notation here, x sub I was to this j here. That would be an infinite sequence in the ith metric space in the product. So the I corresponds to the metric space number, and then the j is the thing that iterates or increments as part of the sequence. And we have a condition that we're going to use in a theorem. So a sequence, so in other words, one sequence for each one of these metric spaces, converges to a point in the product of the metric spaces if and only if each one of the individual sequences, this one converges to this one converges to this one converges to this. So that's a condition. As you can see, it seems like it would be true in most cases, although it's not always true. But if we have this being true, then we have this particular condition. Now it holds true for all the p norms that we defined in the previous slide. So that's the ones that we're kind of focusing on here. If the metric that we define over a product of metric spaces satisfies this condition, then the following theorem gives us a way to determine the open set. So that's on the next slide. So let's look at that. So here we have it. If product metric condition 1, the one we just talked about, holds true for the metric D on the product of metric spaces we have here, then the open sets in our product of metric spaces are the union of product sets of the form y sub 1 cross product y sub 2 all the way to y sub n. So each one of these y's is an open set in the X, and what this theorem is saying is that the open sets in X have this form here. So it's just a matter of taking an open set from each one of these and taking the cross product, and then we get an open set in the product space. Excuse me. So the theorem, I'm not going to prove the theorem, it's rather long and complicated, but there's a book that I reference in my book, which you can download, and you can just click on the, actually you can't click on the reference, it's for purchase, but I believe this book is available for loan from the Internet Archive. So if you're really interested, you could loan it out and just look at this theorem. And we have a second condition, which will give us yet another theorem related to completeness. So given the metric spaces and the product, so we kind of working with the same assumptions here, we refer to the following properties, product metrics condition number 2. And it's saying that the distance for the, the ith distance here for the ith metric in this list is always less than or equal to the distance between the two elements in our overall metric space X, this product here. So that's true for the p norms that we've looked at, and that's why I put this up here at the top. If you take p equals 2, for example, then the distance, say this one here, the distance between x sub 1 and y sub 1, that distance is less than the distance between the two elements here. And you can see that because already if you take the square root of just this one term, you're going to get the distance between x1 and y1, but then you have all this other stuff added in. So the distance between x1 and y1 is going to be less than this here, and the same for any of the individual terms. So this holds for all the p norms. I just showed you one example. And if you have the metric condition, well, I said that. Now, if you have both conditions 1 and 2 holding for a product of complete metric spaces, then the product itself is also a complete metric space. So let me just say that again. So we have a set of n metric spaces that are complete individually, and we take the product, the Cartesian product, and if the conditions 1 that we had in the last slide and 2 both hold true, then the product space is also complete. And again, this is a bit complicated to prove, but I have a reference here to this book, Introduction to Topology by Gamelin. So if you're interested, you can have a look at that.